So today we have a talk by Anatoly Dymarsky, and he's going to speak about classical and quantum codes, two-dimensional conformal field theories, and holography. So please start.
Thank you. Thank you, Dmitry. I'm very pleased to be here virtually, but nevertheless to be able to speak about our recent work. In fact, it's a series of works which we have been developing during last, I would say, 5 years, maybe since before the pandemic. We started before the pandemic, and this work started. Let me go to the next slide. As some continuation of some rather old works by Dolan, Goddard, and Montague. I will review those works a little bit. And even all the works by mathematicians. There is a well-developed theory of classical codes. And for many decades, maybe for 50 years, around 50 years, maybe even more than that, mathematicians know that classical codes are related to the problem of constructing exceptional lattices and related to the problem of sphere packings. And we use these mathematical connections and develop them. And around the pandemic time, I would say at the height of the pandemic, and in early September of 2020, we wrote several papers, which I would say reignited interest in this topic. But more recently, and we will continue writing and developing. But more recently, this past fall, in October, we had 2 more papers where we understood the relation between codes and CFTs from the holographic point of view, and even more than that, we understood that this relation has roots in the higher form symmetries. They're called higher form symmetries. These are symmetries which correspond to extended objects, something like Wilson lines or surface operators. And that discussion sheds completely new light on our previous results. So mathematically, all of our results hold. It just there is a completely new way to understand them. And I assume that you did not follow all of this, but I want to give an introduction into this topic, and maybe logically I should start with some very recent results because they explain really what's going on. But it will be difficult to make connections if you know the history. So therefore, I decided that for talk today, I will start with some historical overview and first explain the logic behind these old papers, and then schematically explain what we did 4 years ago in 2020 and what we did since then. And then I will shift gears and start talking about, and that would be the story about connecting classical codes to CFTs. So the philosophy here is that you can construct interesting CFTs over the Narayan type, if you're familiar with that. If you're not familiar, let me explain what that is. These are the very simple two-dimensional conformal field theories of the kind you can read about in Polchinski string theory textbook. These are very, very simple, actually free field theories which describe two-dimensional string propagating in a multidimensional torus. So from the point of view of CFTs, these are literally the simplest theories, completely solvable, well understood. But nevertheless, you can construct interesting examples of these theories starting from classical codes. And then I will shift gears and explain how this picture emerges from three-dimensional Chern-Simons theories, which are three-dimensional topological quantum field theories, and how this construction is related to identifying the maximal group of non-anomalous symmetries, or using the language of condensed metaphysics, identifying the group of condensable anyons and how to condense those anyons. And once those anyons are condensed, we will arrive at holography. We will describe two-dimensional CFTs in terms of 3D bulk theory, which is not gravitational, but nevertheless, it's a holographic correspondence because you have an equivalence between 2D theory and 3D theory. And while doing that, we will also discover the correspondence between ensemble of boundary theories and a gravitational theory in the bulk. Gravitational in quotes because it doesn't have dynamical graviton, but it sums over topologies. Okay, so this is a bird's eye view overview of my talk. So let's start with some technicalities. I will start with a simplest example, the compact scalar CFT. That's the simplest possible field theory into dimensions you can think of. You have just one scalar field, massless. It is a CFT, but to make it completely finite and avoid any infrared singularities, we say that field phi describes a point on a circle. It's a one-dimensional torus. So we will identify field phi and phi plus r. This is what is called compact scalar. This theory is very easy to solve. For example, to calculate the partition function, you need to sum over all classical saddles. So you need to solve the equations of motion. Oh, I'm sorry. I probably touched my mouse one extra time. You need to find all classical solutions. The equations of motion are trivial. The particle or two-dimensional string propagates on a circle with a constant velocity. And the only subtlety is that this constant trajectory should be periodic on a torus. We have a torus because the world sheet of a two-dimensional theory is a torus. So we should have periodicity. And this periodicity will include R because that's where the particle moves. So this is this R, and this is what is called windings. But you also have 1 over R. These are the moments because your particle has particular velocity, and velocity of a particle in a circle is quantized. That's like standard thing in condensed matter. If you have periodic potential, then the corresponding moment of the particle lives in the Brillouin zone, and you have quantization. So I do hope that many people in the audience are very familiar with the story. This story is described in great detail in Polchinski textbook. It's described in great detail in the what is called Yellow Book about CFTs by DiFrancesca and friends. So there is nothing new about this story. But the thing which is important for me is that once you solve this theory and you see that you have what is called moments, these are not the moments per se. These are combinations of moments and windings. They form a lattice. So if you have PL plus PR, that would be just moments. If you have PL minus PR, that would be just windings. But they're a combination, PL comma PR. That's a lattice in 2n dimensional space. Sorry, what is n here? I didn't explain what is n here. It's not this n, I apologize. This n, in the case of compact scalar, is 1. But in general, n is the number of scalar fields. You can have more than one scalar field, then your string will be propagated on a multidimensional torus of dimension n. And the interesting thing, the important thing is that the combination of PL and PR, they form a lattice. And you can see that here because n and m are integer. And this lattice has very specific properties. It is even and self-dual. So the mathematical statement, which is, of course, very well known for people who encountered Narayan theories before, is that Narayan theories, free scalar CFTs in 2 dimensions, are uniquely parameterized 1-to-1 by even self-dual lattices in the dimension with Lorentzian signature n, n. Okay, so now I want to explain how one can try to construct those Narayan CFTs starting from codes. And we will be constructing only very special Narayan CFTs. The idea is to start from codes and construct a lattice, and lattice will define a CFT. So I need to quickly tell you what the codes are, and in reality, codes are just a bunch of zeros and ones, as one can imagine. So we consider binary strings. Binary strings are literally strings of n zeros or ones. And a string can be thought of as a vector in a vector space, but it's a discrete vector space because the only thing you can do is to add things to each other, and you do all multiplication, you do all arithmetic operations mod 2. So linear code is a linear subspace in Zn to the power n, or in other words, linear code is a combination of binary strings, which is closed on the addition. And then once you have a code, you can construct a lattice. And this is called construction A. You start from the code C, and then you construct the lattice in the following way. You look at the cubic lattice in the n-dimensional space, and then you look at particular vertices of this cubic lattice, and you evaluate, you take the coordinates of this vertex on a cubic lattice and calculate V mod 2. That becomes a binary string. And if that binary string is a binary string from the code, then that particular vertex of a cubic lattice is a vertex in your new lattice. And if V mod 2 is not in the code, then you throw this point away. In this way, excuse me, I have some strange sound here. So in this way, you can construct a lattice based on the code, and this lattice will be a sublattice of a cubic lattice. Okay, so it's very clear from this construction. I'll have next slide with visualization of the story, but the punchline here is that you can construct certain sublattices of a cubic lattice, and you might think that this is not particularly interesting. Obviously, not all lattices are sublattices of a cubic lattice. You might think that only very boring sublattices you might think that only very boring lattices could be sublattices of a cubic lattice, but this is obviously not the case. Because if you start with a code which satisfies certain additional properties, for example, evenness and self-duality, and what is evenness and what is self-duality, if you look at this vector, binary vector, you can multiply it by itself and calculate that mod 2. That will define scalar product. And if you have a scalar product, you can define evenness as the statement that all code words, all strings, binary strings belonging to the code, they are they have even number of ones, or you can in fact define double evenness. That's the number of ones divisible by 4. And you can define self-duality also with respect to the scalar product. I'll maybe skip all of that because that will be important if we go into details of the construction, but conceptually it's unimportant, some additional constraints. And if you consider codes which satisfy some additional properties, your lattice, in fact, will be even and self-dual. And even self-dual lattices are very rare birds. They're very difficult to come by. And the idea that you can start with a code, a bunch of zeros and ones, and construct even self-dual lattice, that's already very interesting, very powerful idea. And as an example, you can start with what is called perfect Hamming 8,4,4 code. This S is a type. It should be just a code. It's a particular code which is very well known in the coding theory. It corresponds to binary strings of length 8, and there are 4 of such linearly independent strings, and it encodes up to it encodes up to 4 bit errors. Then if you start with this code and apply this procedure, you will obtain the unique even self-dual lattice in 8 dimensions, the root lattice of E8. That's just an example that special codes, interesting codes, give you interesting lattices.
Anatoly?
Yes.
May I ask you a question?
Of course.
So connection to conformal theories is only through the fact that the same lattices appear.
Yes. Yes.
There's no any other
information. At this point in my talk, and historically, the only connection to conformal field theories is through lattices. So it's an old logic, but Arkady, since you're very familiar with this, it would be helpful if we start historically. That's how I started my talk. Originally, the idea was, okay, we know very well that Narayan theories are parameterized by even self-dual lattices. If you manage to construct a lattice like that, it will correspond to some CFT, and with some properties encoded by the lattice or completely determined by the lattice. And then if we start with certain codes, we can perhaps construct some interesting even self-dual lattices, which will give rise to some interesting Narayan CFTs. And then we can separately ask a question, what are the properties of a CFT which are determined by the code alone? Okay, that's a legitimate question, and we will answer that question soon. But as you correctly pointed out, in this construction, you start with the code and you go to CFT through the lattice. You don't see CFT until the very, very last piece of your construction.
Okay, thank you.
Okay, that will completely change once we start talking about QKFTs and stuff like that. So that's an old logic. But once you understand the old logic, you will understand the paradigm change. Okay, I also want to bring my phone because I need to know how I'm doing with time. Okay, so I want to visualize the construction. The construction A is very simple, geometrical. The formula is here, but even easier is to visualize things. The idea is that a binary string of length n can be understood as the coordinates of a vertex of a unit cube in n dimensions. So let's imagine you have 3 dimensions. You have coordinate axis. You have this, no, sorry. You have, I'm trying to move my mouse. You have this unit cube. Any binary string, let's say a string 0, 0, 0, that's this point. And then 1, 1, 1, that's this blue point. So if you have a code, the code is the same as a bunch of vertices on a unit cube. If you want to build a lattice, how do you do that? You first mark all of your vertices on a unit cube. In this case, there are 2 blue points. And then you move them in a parallel fashion in all possible directions with a step 2. You do it in this way, you do it in this way, but you also need to do it to the left and to the right, bottom. I mean, in all 3 dimensions in this picture, but I only have one direction for simplicity. Once you do this parallel transport, you will obtain a periodic structure, which is in fact a lattice. You can quite easily show that if your underlying code was a linear subspace, was a linear code, it was closed under addition, the resulting set of points will be a lattice. And then the statement which is important is that if your code is what is called double even, the lattice will be even. If your code is what is called self-dual, the lattice will be self-dual. The same thing visualized one more time. This circle encircles a unit cube. You have points with a coordinate, let's say 0, 0. That's the blue point. You put it in a parallel fashion in all possible ways with a step 2. You have a red point with the coordinates, let's say 0, 1. This is 1, 0. This is 0, 1. You put it in all possible ways with a parallel fashion. And you have a periodic structure, which is in fact a lattice. It is a sublattice of a cubic lattice. This is completely clear. But this lattice is not a cubic lattice itself. It's in fact rectangular. The unit cell is this one. It's rectangular. And the example with the E8 should suggest that, in fact, sublattices of cubic lattice could be very complicated and very non-trivial. Okay, so that's an old story. Now, the question which Arkady asked implicitly, or maybe I inferred this question from Arkady's question. What are the interesting properties of a CFT which I can see directly from the code? One of the basic properties of a CFT, or basic features of a CFT, is a CFT partition function. And for an Orion CFT, you can calculate it very easily. It's a lattice theta series. You have this even self-dual lattice. You calculate it theta series. Then you divided by Dedekind eta functions, some standard functions, and that gives you the torus partition function of your CFT. Now, an interesting thing, a very simple thing, but an interesting thing is that if you want to calculate a lattice theta series for a lattice which is built from a code, then the only thing you need to know is the code. And it's not a mystery, I want to explain how that happens. A lattice theta series is essentially a sum over all colored points on this picture. So there are 2 ways, well, there may be more ways, but there are at least 2 ways to calculate the sum over all points. You can simply go and in consecutive circles, and this is the origin, and then calculate sum over points which are farther and farther away from the origin, and that will give you the standard expansion of a theta series in terms of the powers of q. Q is a standard modular parameter. Q is equal to exponent 2 pi I tau. Okay? But then there is another way. You can first sum over all blue points, and then individually you can sum over all red points. It's very clear that all blue points are avatar of this origin point, and it is related to the code word 0, 0. And then all red points are avatar of this red point, and they're related to the code word 0, 1. So in this way, you see that at least schematically, the sum over all points of your new lattice is a sum of sums where each of these partial sums is related to the code word, to each individual code word. And in this way, you can obtain the following fundamental statement for our story, that lattice theta series can be obtained from what is called a numerator polynomial. A numerator polynomial is a very simple mathematical object which characterizes the code itself. It is a polynomial which simply tells you how many different code words your code has. More accurately, the numerator polynomial tells you how many different code words of different length your code has. But in practice, that's just a polynomial. And then if you take the arguments of the polynomial to be not abstract auxiliary variables, as they usually are in the information theory, but particular Jacobi theta functions, then you will obtain immediately the theta series for your lattice. So we obtain the following statement, that if you have a code and the code is characterized by enumerator polynomial, you can immediately calculate theta function of a lattice, and that immediately gives you partition function of your CFT. And better yet, you can ask, well, partition function, torus partition function of a CFT is a modular invariant, and that's highly non-trivial. That's really big deal. How can I see that from this construction? Well, for this highlighted object to be modular invariant, theta has to be modular covariant. And it is modular covariant because the enumerator polynomial of a code satisfies certain algebraic identity, which is called McWilliams identity, and it is very well known in the coding theory. If your code is self-dual, it means that enumerator polynomial of a code will satisfy McWilliams identity, and that, in a sense, a statement that is this polynomial will be invariant under discrete Fourier transform. Okay, and that too can be explained from the physical. At this point, this is just mathematical statement. You open a mathematical book from 60s or 70s about coding theory. You see they discuss McWilliams identity. You say, very good, that mathematically explains in very simple terms, because this is just a very simple algebraic identity, how this object is modular. But later in my talk, you will actually see that you can derive McWilliams identity from first principles from the physical picture. Okay, any questions about this? Okay, if we have no questions, I want to boast a little bit. What are the results? What can we achieve with this construction? So what we can use, what we can do practically with this construction is the following. We can start with many interesting codes and obtain many interesting CFTs. So one thing which you can do very, very easily is to solve modular bootstrap constraints for the torus partition function. Because as I just explained, if you want to construct a modular invariant guy like this, all you need to do is to construct a polynomial which satisfies certain algebraic identity. And that is very, very easy to do. And that's what we did a few years ago, starting from 2020. We constructed what is called fake polynomials, polynomials which are not associated with any code. We constructed fake modular invariants, and then proved in a paper which appeared, I don't know, a little bit more than a year ago, this paper in 2022, we proved that we constructed what we call fake Z. This is a modular invariant which has all the properties a torus partition function of a CFT would have, which means that it has an expansion in terms of modular parameter Q, positive powers with integer positive coefficients, and it's modular invariant. But this guy does not correspond to any two-dimensional CFT. So basically, we have shown that, if you want to speak about that conceptually, we have shown that doing modular bootstrap at the level of torus partition function is not powerful enough to distinguish between bona fide CFTs and fake mathematical solutions of modular bootstrap constraints. That's one thing. Another thing which one can try to do is to construct isospectral theories. There is a very, very famous mathematical story. I even have here a printout from the paper, famous paper, Can One Hear the Shape of a Drum? The question is, if you have a Laplacian on a manifold with a boundary or a closed manifold, can you uniquely parameterize the manifold by the spectrum of the Laplacian? The answer is no. There are known counterexamples. They are constructed with help of what is called isospectral lattices. These are lattices which have exactly the same spectrum or exactly the same lattice theta series, but they're not isomorphic as lattices. That story goes back to Milnor. And in string theory, people know this example very well because there are lattices in 16 dimensions. One of them is a lattice E8 plus E8, and another is what is called D16 plus. And the fact that they are isospectral led people in the 90s to show that they actually correspond to dual compactifications of string theory. So these are two seemingly different compactifications of string theory, but in retrospect, they're physically the same. They're dual to each other. So that was a famous story, but in our paper, we constructed many more examples of isospectral two-dimensional CFTs. In fact, we constructed hundreds of them. We have a generating machine which generates those polynomials, and if the two polynomials have the same spectrum, well, if two codes have the same polynomial, it means the corresponding CFTs will be isospectral, and we generated so many of them. There are more than one. There are more than one can process. So that's the result of this story from 2020. And then also, oops, I'm sorry. And then also there is this connection, more general connection to conformal bootstrap program. Conformal bootstrap program is very heavy on numerics, and people do linear programming bounds. And all of that has its counterpart in the coding theory. And in fact, it predates conformal bootstrap by decades. In the context of information theory and the coding theory, you can also ask what is the best code, what is the best Hamming distance. Hamming distance is a characteristic of a code which specifies how much information it can preserve. And the problem of finding the best code is dual or counterpart of the problem of finding CFT with the largest spectral gap. And then at the level of codes, the linear programming bounds were developed by de la Sater in 60s, and that's called the de la Sater problem. And you can easily see that if you start with a conformal bootstrap and restrict yourself to the family of Narayan theories, and even more so to the family of code CFTs, what we call code CFTs, CFTs obtained from the codes, then you literally reduce your modular bootstrap story to this famous de la Sater linear programming bounds. And the interesting thing is that de la Sater's linear programming problem is still not solved as a mathematical problem. People still don't know what's the optimal rate, what's the best, if you increase the length of the code, what would be the best rate with which you can safeguard information. And the analog of this question is that people still don't know if you increase the central charge of a CFT, what's the maximal spectral gap. People have a guess, not in connection with this Narayan CFTs, but people have a guess that in general CFTs, if the central charge goes to infinity, the spectral gap cannot be larger than C divided by 6. No, C divided by 12. That's the BTZ black hole threshold. And there is an analog of that for the Narayan theories, but proving that is very difficult. Nobody knows how to prove that. And the same thing, nobody knows how to establish optimal bound for de la Sater's linear programming bound. The most recent improvement was in late 90s, early 2000, by two people from St. Petersburg, I think, at the moment. That's a very technical paper about solving this linear programming bound. And it's not clear if their bound is optimal or not, meaning if it's the best one or not. Okay, anyway, these are the details. Unless you're really interested in information theory and connection to information theory, they're probably not very important. So I will stop the first part of my talk and invite you to ask questions. And after the break, short break, I want to start with a new picture, the physically motivated picture. Any questions? Okay, assuming there are no questions, let's move on and let's talk about something completely different. I want to talk about ADS-CFT. ADS-CFT is a story when you have a theory in the bulk and it's physically equal to theory in the boundary. Usually it works in the way that you have you have partition function on the boundary and it should be equal to the partition function in the bulk. But the bulk is usually can be understood, let's say, in unequal force superring mills and ADS5 crosses 5. ADS5 can be understood as a theory with the space with the boundary. And therefore, instead of calculating partition function in the bulk, you can say you're calculating bulk wave function. And therefore, instead of writing ZCFT is equal to Z bulk, I can write ZCFT is equal to psi bulk. That's a standard understanding of ADS-CFT. There is a more recent, interesting twist, when instead of a particular CFT on the boundary, you have an ensemble of CFT on the boundaries, and then you still equate that to the bulk. And it's not entirely clear how this story is related to this story, but we will talk about that. So that's that's the ADS CFT. That's a story from 1997 from Aldesena's conjecture. There is an 10 years older, so there is a story which is 10 years older from late 80s, coming from the work of Witten, which relates Chern-Simons theories to rational conformal field theories. And the story there goes like that. If you have, let's say, 3D Chern-Simons theory on a manifold with a boundary, then the wave function of Chern-Simons on a manifold with a boundary is not a partition function of a CFT, but what is called a conformal block. It's a part of a partition function of a CFT. So it looks similar to this, but it's not the same thing because conformal block is not the full CFT. And in fact, if you want to build the full partition function of a CFT, you usually need to combine those conformal blocks in bilinear combinations or something like that. So this story is similar to holography, but not literally holography. So first immediate question one can ask, what's the relation between Chern-Simons RCFT relation, duality, if you wish, to holographic, there is a typo here, right? To holographic duality. The relation was maybe known to some experts, but not widely known in the literature, I think. And we had to reinvent a bunch of wheels. And we had a paper with Al Shapir and Ofer Aharoni just in October, working that out for abelian Chern-Simons theories and Narayan theories. But basically, the question we started from is the following. The standard relation by Witten is between bulk wave functions and conformal blocks, while what we need is a relation between bulk wave function and full partition function. So we need additional ingredients which might be built in terms of a surface operator, but we don't want a surface operator. We want thermal ADS closed manifold with no insertions, and we want some theory here. So that's the discrepancy. Okay, Right, but instead of trying to explain from the first principles how we solve this discrepancy, I maybe want to give you an example, and the example will come in the form of Kitaev's story code. So for many different people, Kitaev's story code can be understood differently. For some people in condensed matter community, Kitaev's story code is a two-dimensional physical system which has 4 times degenerate ground state. For us, in our talk, in this talk, you might think that time goes vertically and radial coordinate goes to the right, but now you need to invert that in your head and think that time goes from the left to the right, and therefore all of this boundary slice is a spatial slice. That's a two-dimensional spatial torus. Then you will obtain exactly the picture on the slide. You have two-dimensional spatial torus. You have physical system like a lattice system which lives on a two-dimensional torus. It's 4 times degenerate. And on the next slide, I will explain, and that's very well known, that it is described by Chern-Simons theory, but you can forget completely about Chern-Simons theory and think as a condensed matter physicist. You have a 2-dimensional, 2 + 1 dimensional physical system. It has a 4-time degenerate ground state, which physically is a space of 2 qubits. Each qubit has 2 states, and therefore 2 by 2 is 4. And you have topological operators, Wilson lines in terms of a Chern-Simons, and those Wilson lines can form cycles over one of the 2 cycles of the torus. Cycle A is red, cycle B is blue, and there are 2 different Wilson line operators, or in terms of anyons, if you know Kitaev's toric code the excitations above Kitaev's toric code are anyons. So there are 2 anyons, electric anyon and magnetic anyon. So you have 2 Wilson lines which can wrap each of the 2 cycles. Therefore, you have 4 Wilson lines. And in terms of quantum operators acting on 2 qubits, these are just these guys. These are either Pauli Z matrix or Pauli X matrix. Okay, and then how is that related? How is that related to the previous slide? The idea of what we are going to do is the following. I will try to first illustrate the idea. I'll first try to say that if I have non-trivial Chern-Simons theory, or described in the toric code, or if you simply want to think about toric code, you have non-trivial anyons. and I want to, what condensed matter physicists say, I want to condense an anion. What does it mean to condense an anion? It means that the corresponding particle is acting trivial on the Hilbert space. Or mathematically, it means that I have two Wilson lines, electric Wilson line, this one and this one. It means that I have electric charge and it goes along this cycle or this cycle. And I will say that I want, and I want a state in the physical Hilbert space of a vacuum of 4 times degenerate vacuum of Kitaev's toric code, on which any operator which involves electric anion will act trivially. In other words, what I want is a state on which both of these guys act trivially. So if you're a little bit familiar with the quantum code, you immediately see that what I formulated is a stabilizer quantum code. I have two quantum operators acting on two qubits. They're mutually commuting. It has to be the case because electric anion will commute with itself no matter which cycle it is wrapping. And I want to find a state. In this case, it's a unique, I'm playing with the mouse and that moves us around. And I want to find a unique state which is an eigenstate with an eigenvalue 1 to both of these Wilson line operators. So from the point of view of condensed matter, I condensed the anion E. From the quantum information point of view, I found the stabilizer state, which corresponds to stabilizer code. The part which is non-trivial and related to holography, and which probably was known to very few experts, was not written anywhere explicitly, and now it is written in general terms, but explicitly in our paper with Offer and Alfred, is that if you look at the state, as one of the states in the Hilbert space of the vacuum of Kitaev's toric code, and you ask, what is the holomorphic representation of the corresponding wave function? This is a representation of this wave function in terms of qubits, but you can go back and remember the Witten story about conformal blocks and blah blah blah, and you can invoke this picture. And you can ask mathematically, what is the holomorphic representation of this wave function psi e? It's the same function psi e. You will immediately understand that this is a partition function of a compact scalar of a particular radius. Okay, and that gives you desired holographic correspondence, because now it's not a conformal block, now it's a full CFT partition function. Okay, so this is something I would say non-trivial. If you never heard this talk and never read my papers and not an expert, if you never read some specific papers by Greg Moore and reading between the lines of those papers, this statement might come as a surprise. This is what we believe is a novelty here, that if you condense electric anion, the corresponding wave function is actually, it has holographic meaning as a CFT partition function. Okay, you can immediately ask, what is the radius here? What is the radius of a compact scalar? The answer is, it's up to you. There is a freedom of specifying boundary conditions, if you wish, in your topological quantum field theory, which is a Chern-Simons theory. So you can choose this radius to be whatever you want. It's like in quantum mechanics, you can have more than one representations of your wave function. Say you can have momentum representation, coordinate representation, or something in between. So is here, you have a continuous family of representations. So this R could be anything you want. But that's not the end of the story, because similarly to what we did with condensing electric anions, we can condense magnetic anions, and that will give us a stabilizer code built with these two stabilizers. There will be a different wave function not written here. It will be 0, 0 plus 1, 0 divided by square root of 2. That will be the magnetic wave function. And that magnetic wave function will be given, it will be equal to the partition function of a CFT with a different, of a compact scalar with a different radius. This R is arbitrary, but the relation between this radius and this radius is fixed. So the variable R could be whatever you want, but this guy will be twice smaller than this guy. And that's crucial. So that tells you that this holographic duality cares not so much about describing a particular CFT, but describing an ensemble of CFTs. Only when they come as group that becomes meaningful, because if they come as an individual theory, you can dial R to be whatever you want, and an individual wave function on the Chern-Simons side will describe any Narayan CFT you want. Okay, that was quite a bit of a shift in my presentation, and I was not very systematic going from TQFT to Kitaev story code. And if that's the first time you saw Kitaev story code, it's probably difficult to follow. So I want to ask if you have any questions about this. It's a bad sign. No questions is usually a bad sign at this point. Okay, anyway, so let me reiterate the statement. The holographic duality here it works in the following way. You have a compact scalar CFT, and the partition function of a compact scalar CFT is the boundary wave function of an abelian TQFT after anion condensation, okay? After anion condensation. The same thing can be described in terms of Chern-Simons theory. You start with AB theory with a level 2, because it's 2 divided by 4 pi, so it's level 2. Maybe I should have written it as 2 divided by 4 pi. And then you need to, if you want to have holographic quantization of Chern-Simons, something rather standard, but it's rather standard when you have one field, ADA. Here you have 2 fields. Then, in fact, once you have 2 fields, you have a freedom how to specify boundary conditions, and this freedom is parameterized by an arbitrary real parameter. That arbitrary real parameter will be eventually the radius of your compact scalar. After you gauge correspondence symmetry, you will have a Chern-Simons theory at level 1. So it was 1 divided by 2 pi. Here it's 1 divided by 4 pi. This theory is trivial as a topological quantum field theory, but since it has non-trivial boundary conditions on the boundary, it gives rise to an Narayan CFT, and we work out that in great detail in the paper with Alan Offer, and we calculated partition function on a CFT side, something very standard, what you can read off from the yellow book. And we calculated partition function on a Chern-Simons side, and you match, and there is a holographic dictionary, how you couple these fields. You can ask the following question. You have fields A and B. If it's a holographic correspondence, what do they couple to on the CFT side? There are 2 gauge fields. There will be 2 boundary conditions, and they will naturally give rise to 2 different fugacities in the Narayan CFT. Or another way you can say it, that a scalar can be coupled to gauge field in 2 different ways. You can write something like d mu x a mu, or you can write d mu x veg a mu, right? Or d mu x a nu epsilon mu nu. There are 2 couplings, so in fact you can couple your scalar field to 2 different gauge fields, and these are gauge fields A and B exactly, and we work this out in detail.
May I ask a
Yes.
question?
Yes.
So this, well, first irrelevant question. What is a supersymmetric version of that relation? Because you can write these Narayan CFTs in, I don't know, supersymmetric heterotic case or whatever.
It's a good question. I would say probably. I never thought about it. You probably would have to put something in the bulk, like which would couple to fermions. That might be Chern-Simons theory at the odd level. I mean, well, it depending on your normalization. It could be Chern-Simons theory with the odd level or odd level, odd or half integer level, depending on how you normalize things. That is usually giving rise to fermionic degrees of freedom. But we never thought about supersymmetric.
This is like, I don't know, like ABGM theory would be.
You see, the real question is, you can ask, what are the theories which I hope to describe with Chern-Simons in the first place? Chern-Simons is very simple. It's a free theory. Abelian Chern-Simons is a free theory. So you should only expect that to work if you describe free theory on the boundary. Narayan theory is free theory. Some fermionic theories are free theories, and we say in the paper that we believe you can describe them this way, although we did not work it out. A supersymmetric version of a Narayan theory, I don't remember exactly. You're talking about heterotic string. I have forgot many details of that. Didn't think about that for many years. Is that free?
Well, in a way, it is free. It must be free.
It might be free. So maybe that can be described, but ABGM is not free. So
yeah, no. In abelian, well, if you
yeah.
have a abelian gauge group, if you have a
yes. So all of this probably going to work for abelian. For non-abelian, we can discuss toward the end of the talk, but story is obviously much less trivial.
Okay, and another question or comment. Is it fair to say that this relation is more like repackaging of the same amount of information? It's not really kind of, in a sense, it's trivial example of
Holography?
I wouldn't call this I wouldn't call it holography. It's just relation indeed between say, like
right.
Witten and Chern-Simons theory. Would you call it holography? It's relation between bulk and boundary, yes, but it's more like rephrasing the same amount of information in different ways.
So, okay, I actually want to discuss this a little bit because you expressed the criticism, which I heard from some people in private, meaning we didn't have a chance to, I mean, it wasn't like a criticism of my talk, it was a criticism in a sense that I did not really have a good chance to understand what they meant. But it's not about like it's not like being very defensive about our work. It's really trying to understand what your question entails. You mentioned two things, that we repackage the same information, and you wouldn't call it holography because of that. And second thing you say with Witten and Chern-Simons. So with Witten and Chern-Simons, the standard story is that you have Chern-Simons in the bulk, and the boundary state, a wave function of Chern-Simons in the bulk, is not the Witten. It's a conformal block of Witten. Okay? Our story is different. We are not telling you.
Yeah, I understand. I understand. This is more, in some ways, more direct. Yes.
No, so this is a crucial thing, that we tell you the full partition function. Now, you can say, especially in the light of more recent activity, which became it probably has been known for people forever. It has been written very explicitly for 10 years in the papers by Kapustin and Saulina, and during the last 5 years, that's written in thousands of papers, that you can easily combine conformal blocks by inserting a surface operator. And if you insert a surface operator, you can combine those conformal blocks to produce a partition function. But that will not be holography in my book, because the bulk geometry is that one of an interval. You have a torus multiplied by an interval, and you have one boundary, which is a torus, where your CFT lives, and you have another boundary of an interval where your surface operator lives. That looks nothing like ADS CFT because there is no ADS. Our story is mathematically related, but in the abelian case, you can morph this, what is called sandwich, whatever, this interval story. You can morph it into this picture where you have ADS and you have bulk theory, a trivial, topologically trivial Chern-Simons theory with two fields, A, B. Literally, this theory living in thermal ADS. Okay, and therefore it's different from the standard Witten story of late 80s. That's one part of my answer.
Just 1 second. So yeah. I missed this. So when you say Chern-Simons in thermal ADS, Chern-Simons is topological, so it doesn't care about conformal factor of the metric. So it's not really ADS; it's conformal class of ADS. Or
yeah, of course. It's In fact, since it's topologically trivial, it cares very little about whether it's ADS or BTZ black hole or any of SL2Z avatars of BTZ black hole. The answer wouldn't matter. It's a topological theory. And immediate question you can ask, how does it even know what it is equal on the boundary? It's because on the boundary, in addition to this term, I regret I don't have it here on the slide, but in addition to this term, which is a 3D term, you have a term on the boundary in the form A modulus squared integrated over the boundary. Okay? And that term is metric dependent, and that breaks topological theory down to conformal theory.
Okay, so it's boundary terms and boundary conditions which are
correct. Correct. And now you have another criticism, which is okay. That's a valid point. You say that's rewriting the same thing. So, and I heard this argument. So I would like to ask you how do you define holography? What is holography for you?
Okay, well, the non-trivial statement of holography is that there is a duality where you have some modulus or coupling, and you're really looking at different regions in this coupling. There is example, even the trivial example like free CFT at the boundary and some higher spin theory in the bulk, it still has a parameter like n.
Correct.
So here you don't even have that n.
No, you do have. You do have. Of course, the example you mentioned with, I think, Vasilyev's theory, it's a highly non-trivial example because on a boundary, it's simple. In the bulk, it's so complicated to the extent I know people still could not solve it, right? Or maybe,
I agree, but
right.
it's kind of in a way.
But my point is that this is a psychological problem or sociological problem. Let's say we can have a genius who would come and solve Vasilyev's theory, right? Or would solve string theory on ADS5 crosses 5. And then presumably that solution will give you on the nose unequal force superior nils. So it's more our inability to solve the bulk or solve the boundary if your bulk is weakly coupled, which makes this duality interesting. But interesting is a separate statement. I'm not saying this is an interesting duality. If you're not interested, that's fine. I'm just saying this is a holographic duality. And my definition is the following. It's a duality between two-dimensional theory where I can clearly formulate degrees of freedom in 2 dimensions, and three-dimensional theory where I can clearly formulate action and degrees of freedom in 3 dimensions. And if you calculate partition functions or even correlations of local operators and stuff like that, it will match. And I do have an example here because a 2-dimensional CFT has this action in 2 dimensions, and 3-dimensional Chern-Simons theory has this action with a particular boundary term. And yes, both theories are free, and therefore you can readily solve both of them explicitly and see that they are equal. And if you want, since there are free theories, while solving them, you can even try to relate one to another. And Arkady, you know this about this more than other people. And I'm saying that because when we try to solve this, you do not arrive at the standard scalar field action. You arrive at what people call Littinger action, with the action d0 phi, d1 phi. But apparently, the graduate student who worked with us found some very helpful works of yours dealing with this. So presumably you know how to relate bulk to boundary better than anyone else. But it's only thanks to you that we know this. And I'm just saying that if someone can solve an equal force theory, it will be conceptually the same situation.
Okay, no, I was not. It was not a criticism. I was just trying to say that there are harder examples of duality, like S duality of n equal 4 superior nils.
Sure. This is a straightforward. This is a straightforward duality. I'm not saying that we added much to solving either bulk of the boundary, because in both were solved in a sense. We mostly explain how to package them the right way. Okay.
Okay, thank you.
There is another criticism which people throw away into me, saying that the bulk theory doesn't have dynamical graviton, and that's why it's not holography. But that requires a definition of holography to be rooted in gravitational bulk. And that's a separate thing which can be discussed separately. Okay, all right. Dmitry, how much time do I have at this point?
5 minutes.
Only 5 minutes? Okay. Okay, that's tough. I will skip the general case. I'll skip the general case. Then there is a story which I probably want to explain how to understand all of that from the first principles. But the idea, how codes emerge in the first place, the idea is that you start with a TQFT or Chern-Simons, and you ask yourself, what is the maximal non-anomalous group of one-form symmetries? Or in other words, what is the maximal group of condensable anyons? And since the theory is abelian, you will immediately arrive at something which is literally the classical codes we started with. And then by condensing the anion, you will immediately see that you construct the code CFT with the lattice given by this formula. And basically in this recent paper from October, it's a very short paper, 4 pages. We try to explain that you didn't have to know anything about codes. You can start with TQFT and try to identify maximal subgroup of non-anomalous symmetries and then try to condense it to obtain a boundary CFT, and you would reproduce our code CFT construction. Okay, so that really gives a physical picture behind our works, behind the works by Dolan and people like that. Okay, but I also want to move beyond that and actually talk about more interesting version of holography, which maybe will be of interest to Arkady. And the idea how to go between the surface operator and theory in the bulk has quantum information aspect to it. If you want to condense anions, what you need to do from the quantum information point of view is to construct a quantum code. We saw that in the case of Kitaev's code. And then once you construct a quantum code, the statement could be either between a particular code CFT and trivial topological theory in the bulk, or better yet, you can discuss ensemble holography. And ensemble, I only have 5 minutes, maybe less than that. There is a rather famous story now about averaging over Narayan theories and getting something like U1 gravity. But I want to give you, I really have no time talking about that, but I want to give you a taste of it in case of Kitaev story code. And in case of Kitaev story code, we saw that there are 2 ways to condense anions. You can condense electric anion and you condense magnetic anion, or we can discuss different topologies. You can put Chern-Simons theory behind Kitaev story code on a 3-dimensional manifold which ends with a torus, but torus has one of the shrinkable cycles. You can either shrink A cycle or B cycle or A plus B. You cannot shrink any other cycles because this is a Z2 theory, and modulus Z2, there are only 3 combinations, A, B, and A plus B. And then you can mathematically check that you have an ensemble holography. You average over your code CFTs, and that's the same as the sum over topologies. Okay, in our paper with offer, we have an infinite series of these things for ZP and stuff like that, but it doesn't matter. We have, for Kitaev story code, we have an example of ensemble holography. You have an ensemble of 2 CFTs, and in the bulk, you have Chern-Simons theory summed over all possible topologies. Okay, and then we have a generalization of that for many, many complicated things, and this is related to mathematical statement of Hove duality. And I will probably, I don't probably have time to describe all of that, but this is a statement. You have an ensemble of CFTs on the boundary, and you have sum over different topologies in the bulk, and you have TQFT, which you sum over different topologies in the bulk, and TQFTs don't care about morphing continuously, but they care about topologies, and therefore you have different wave functions, and you need to average over all of them. And with this rush through the last slides, I arrived at my conclusion. So the new picture, physical picture, is that codes encode condensable anions or non-anomalous subgroups of one-form symmetry, and in that way they give rise to code CFTs. They reproduce our old construction with lattices, exactly reproduce, but from this first principles approach, starting from anion condensation. Second thing which we understood recently, and I had very little time to talk about it, is the holographic duality when you have an ensemble of code CFTs, not a particular code CFT, and then in the bulk you will have Chern-Simons theory which sums over topologies, and we understand that very clearly from the Narayan theories. But then a question which one immediately has, can we go beyond the Narayan theories? And we hope that there is a connection between, there is an extension to the story to TQFTs with non-invertible symmetries. We can go to non-abelian TQFTs with Zumina-Witten theory, or rather in the bulk that is Chern-Simons with SUN. But even beyond that, we believe that Virasoro TQFT or even JT gravity can be explained through our framework, that you have TQFT in the bulk, you need to analyze condensable anions and consider a thing which I should emphasize. It's emphasized in our paper. It hasn't been emphasized in the talk. You need to consider an ensemble of all possible gaugings of your bulk TQFT, or an ensemble of all possible condensations of anions in your bulk TQFT. That will give you an ensemble of theories on the boundary, and that ensemble, we claim, has holographic interpretation, as being dual to a gravitational theory which sums over different topologies. I understand that that wasn't maybe crystal clear, and I skipped a lot of details, but I have to stop now. So thank you very much.
Thank you. Are there any questions?
Yeah, may I have very little understanding of what I'm going to say, but there is a picture of which generalizes Maloney and Witten's story about partition function of Einstein gravity related to well, where you sum over different
yes,
where you sum over topologies, including wormholes, which is related to averaging over CFTs at the boundary. So this is in the context of ADS3, Einstein gravity with cosmological constant. And
yes.
So is there any relation to what you were just saying, or?
There are two Maloney-Witten stories. There is a Maloney-Witten story about more standard gravity, and that story started in 2007. And there is a more recent story in 2020 when they summed over 3D theories, but matched that to Narayan CFTs.
Yeah, that's what I meant, the more recent ones. Sorry.
The more recent one, the Narayan CFT, we, in a paper with Ofer Aharoni and Al Shapir, we have shown that their story emerges as a limit of our story when we consider literally as a limit. We solved one of the problems they had because their theory in the bulk, when they have a formal sum in the bulk, which does look like a sum over topologies, but the underlying Chern-Simons theory was not well defined because it's neither, the gauge group was neither compact nor non-compact, because both would give you wrong results. So we explicitly have shown that their story is the limit of what I was talking about today. You always have a compact group, but once you increase the level of Chern-Simons to infinity, you reproduce literally what they have. That's described in great detail in our paper with Alfred and Ofer. Of October there are two papers which came out in October of this year.
But I guess my sort of interest was related to the aspect that if you include wormholes into this partition function in the path integral.
Very good. That's a great question. They did not add wormholes to partition functions, or at least they did not add all wormholes to their partition function. They had two problems which they complain about. First, they could not really say what is the microscopic theory in the bulk. Second, it was not clear why they sum over certain topologies but not over others. Okay. So first problem we solved in this previous paper in October. We said that there is a compact group Chern-Simons theory, and you obtain their result as a limit. Second problem we also solved, but not in the previous paper, but in the paper to be written. This is something unpublished. This is not anything on the slide, but one can show, this is my claim, that in fact one has to sum over all wormholes, but because of the theory is abelian and blah, 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 one ends with the sum which they have in the paper. So they don't see the sum over all wormholes. They sum only over specific topologies, but that's just a particular story, a particular case, a simplification. In reality, one has to start with the sum over all possible topologies over all possible wormholes. Okay, so our story fixes both of the problems they had.
Okay, thank you.
And there is another story by Maloney and Witten when they really deal with gravity and boundary ensemble of CFTs is not clear. This is what is called Virasoro to QFT. That is not an abelian to QFT, but one can hope that's not solved. That's more like a wish that one can apply our framework to that story, and pending ability to solve this non-abelian to QFT, hopefully one can arrive at and rederive Maloney and Witten and fix it, because it also has its own share of problems like negative density of states and blah blah blah. But that's more like a to-do list, a program for the future.
Okay, any other questions? Well, I had a naive question. So do you have a stress energy tensor in the CFTs?
Yes, you do. But these are very simple free CFTs, and the stress tensor is fully made out of conserved currents. I worry that I will embarrass myself, but I think this is called Sugawara stress tensor. The idea, this is very well known in string theory textbooks, and I studied that. I just forgot these things. So the idea is that you have conserved current, like d mu phi is a conserved current, and then you can use conserved current to build the stress energy tensor, which means that this is not an independent operator. Okay, so you do have stress energy tensor in field theory, but you don't have a graviton in the bulk. Instead, you have something dual to a conserved current, and that is the gauge field. Or in the bulk, you can fantasize and say that you have a mu, and you combine it into a mu, a nu, and that will be something like G mu nu, and you can play this game, but it's not a dynamical gauge field. So Witten did this he played this game reformulating classical gravity in ADS3 in terms of SL2R across SL2R. You can play this game for conventional U1 Chern-Simons, but that graviton will not be, that G mu nu will not be dynamical. So there is not clear what you will learn from this.
Okay, I see.
Okay.
Okay, the last call for questions. Okay, so we don't have any further questions. Thank you very much.
Thank you.
Thank you. Yeah, thank you. Bye.
Bye.